So where we left off with acoustic emission, we were looking at the installation of the actual systems, kind of the construction, what the major components are. And I was talking about, a most basic form. Let me go back one slide. Most basic form is we have our sensor, some kind of preamplifier, usually has filters. We're going to further amplify that signal and then perform measurement and analysis and an output. Most of the time, these sensors aren't going to be used by themselves, but rather you're going to have multiple sensors that all feed into a single system, and then are able to provide a little bit more in addition to the qualitative data that something happened, they can start to provide a little bit more quantitative data like location or some idea of amplitude or the amount of change. So finding that source location, we were talking about homogeneous versus non-homogeneous materials and shapes can play a role in it. And so homogeneous and regular materials, sound's going to transfer evenly through them. And so those are the easiest to kind of pinpoint sound versus non-homogeneous materials because of all the acoustic interfaces we have. We get sound sections, we get one form of, different forms of attenuation. That can affect it. And so we have to keep that in mind when these systems are designed. They're designed with the sound transmission of a specific object taken into account. But determining that, there can be three kind of primary methods that are in use out there. Now, obviously, there's research being done where people develop all kinds of other methods or hybrids or things like that. But generally speaking, the three common types are linear, zonal, or point. And so for linear, and if you're familiar at all with how things like GPS or triangulation works, this should look familiar to you. Okay. Do you guys study GPS triangulation in avionics class, right? Based on time it takes for a signal to go from the satellite and back. If you have two satellites, you can put your position on like a ring or a line. If you have three satellites, you can start to do it in two-dimensional space on a plane. If you have four satellites or more, you can start to do three-dimensional space with altitude as well. So works the same way with the sensors here. So if we have two sensors, we can basically look at, what's the ratio of time? How long this crack formed? It's going to reach the closer sensor shown here with this blue one on the right. It's going to take longer to reach the sensor on the left, or this other, my other example here where the source is further to the left. The sound's going to reach, and this is assuming a homogeneous material, the sound's going to reach the sensor on the left faster than it's going to reach the sensor on the right. And so based on kind of the ratio of those times, you can figure out, where that is ratio-wise between the 2 points. Now, these are showing linear, but if I put these on a plane, if I have a two-dimensional plane, and I draw two sensors on it, right, I have a sensor here, and I have a sensor here. This can give me the ratio between them. So essentially what would happen is if we have some kind of a flaw, whether the flaw occurs anywhere along this line, you're going to get roughly the same ratio of sound transmission, for instance, right? So I can have a flaw if I get a crack that occurs here, or here, or here, the ratios between how long it takes the sound to reach each sensor is going to be the same. So it can give me this position as between the two sensors, but it can't necessarily tell me which direction it is on this line, okay? Now, to increase that accuracy, then the next, the next thing that came out was, and it can also work beyond too. If you have two sensors, that was one thing I didn't show here, but say my sensors are a little bit closer together, and I get a flaw that occurs over here to the right, the sound's going to take a certain amount of time to get here. It's going to take longer to get over to here. And so you can know it's somewhere, but it's going to be outside, but it can't tell you, it can kind of tell you where it is on almost like an arc, over in this area. It can't tell you a specific location. So in order to better determine location, there's two ways we can do that. One is particularly if you have a material that has a high amount of attenuation, it doesn't transmit sound very well. The sound may not travel very far, whether it's because it damps the sound, because it scatters the sound, or just because the diffusion of the sound is too great. Remember, there are three elements. that make up attenuation in material. Okay, damping is the resistance to the wave traveling through. The scattering is, you know, in a particularly non-homogeneous and irregular shape, it's going to cause the sound waves to kind of scatter. And then diffusion is the further away you move from the source, that same amount of energy is spread over a greater area over greater volume. And so the amplitude goes down. So those three parts that make up attenuation, if you have a high attenuation material, sometimes it's hard to put the sensors close enough together that you accurately get an acoustic event picked up by more than one sensor. And so that's where this zonal or sensor array comes in. So what's happening here is if we get a flaw in this material, it's only really going to get picked up by one of these sensors. Right? And so if you get a flaw in the zone here for sensor 2, it will attenuate too much before it reaches sensors 4 or sensor 5, right? Or even sensor 1. And so sensor 2 will pick it up. It'll tell you that the flaw is somewhere in this, you know, this zone, this cell, but it won't tell you where in that specific cell it may be because it's only being picked up by that one sensor. Okay? And that is, again, in a high attenuation material where the sound will not travel far enough to be effectively picked up by more than one sensor. Or if it's somewhere in the sensor 4 cell, you know, it won't be strong enough to travel to any of the other sensors. You won't know if it's near the top or the bottom, left, right, whatever. But we know it's in the sensor 4 cell. In materials where the sound's going to travel a little bit better or where you have more sensitive sensors, you know, this was mainly a cost thing today. Sensors, you know, the price of them has gone down substantially, like all electronics, but there's still a cost to install them. Now you can start doing 2-dimensional and 3-dimensional sensor arrays, which allow you to pinpoint a location, whether it's on a 2-dimensional plane or within a 3-dimensional object. And so it allows you to fairly accurately, with some of these, particularly if you have a homogeneous material or material that's been really well studied where you know how the sound transmits through it really well, you can pinpoint quite accurately where the flaw has formed based on how long does it take for that sound to travel, you know, to each sensor. And so signal received, if you get 2 sensors, you'll get a linear determination like I showed here. 3 sensors will tell you a plane, right? It'll tell you the plane, but it may not be able to tell you the depth. Might be at different depths, but then a plane. And then 4, you can get that volumetric, that 3-dimensional determination, just like when you're dealing with something like GPS, we have 4 satellites. You can figure out altitude in addition to latitude, longitude, and then also the change in speed. So here we can look at the position by measuring those different arrival times. You can also look at the difference in amplitude. And I didn't mention that earlier, but not only are we looking at arrival times when we're picking up, but, you know, in the case like what I've drawn here on the board, the sound is going to be, you know, stronger. You're going to have a greater amplitude signal hitting point A than point B because it's going to have a greater amount of attenuation due to traveling further through the material. And so by comparing those, the times, you know, when the sound arrived, as well as how strong the signal was, you know, comparing them between the sensors, right? Because you don't know, you don't have a sensor right on the spot where it occurred, right? So you're comparing the sensor that picked it up the strongest and the earliest to the one that picked it up second strongest and second earliest to the one that picked it up third strongest, third, you know, they're all kind of comparing to each other, but it can give you an idea. It can tell you where that occurred. So, and that's known as triangulation. Okay, basic, you know, the basic technology behind it is triangulation. Same thing used for location finding, but with new equations, algorithms, different ways of doing analysis, they've actually gotten very, very accurate position measurements in a lot of materials. Okay. So when we're looking at the stress application, right, we have to have an object under stress in order to generate these acoustic events. There's 2 main types. So the first is a independent event. Here it shows like a tool drop. It could be, you know, an independent event is something that you're not causing specifically to create that acoustic event. So it can be your vehicle's driving over the bridge where you're doing acoustic emission monitoring. It could be a bird strike hitting the leading edge of the wing. It could be the vibrations from machinery on the aircraft, or rain or things like that, right? The structure is something that's just going to be there naturally. Okay, it could be in a building. It could be wind hitting the building, causing the building to sway, right? And you're monitoring the sounds, the sounds that are given off by the materials as they're flexed and stressed. That's compared to a controlled event where you can actually use very similar. What does this look like? If we look at this right here, what does method 2 look like? Just looking at that, what does that look similar to? You got a transmitter, an actuator, piezoelectric, puts the signal into a part, and then what? It looks like ultrasonic testing. It's almost the same as ultrasonic testing. The one difference, though, is we're not necessarily looking at the sound wave given off by the actuator. Here, the actuator creates that physical vibration that stresses the part, and we're looking for the sound that stress being applied gets generated by the part itself. Okay, so we're not looking at the sound wave traveling through the part as much as we're looking at what's the result of basically vibrating the part. You put a vibration into the part, that's a form of stress. Then the part may give off its own acoustic signals, and that's what we're looking at. Okay, but it's being intentionally done, right? It's something we're controlling, so it's a dependent or it's a controlled event versus an independent event. Independent event is just using what the normal stressors in the environment are: wind, vehicles, bird strike, foam strike. Anyone know what I mean by foam strike? If I say foam strike, anyone know where that's referring to? Because this is one of the first applications for this method that was widely used. What's that? FOAM, foam, like foam strike. You laugh, it was a serious problem. So the Columbia orbiter that disintegrated on reentry was caused by a foam strike. It was a piece of the foam that broke off the orange fuel tank, hit the leading edge during liftoff, and it punched a hole in the leading edge. So after that, they put acoustic emission equipment in the space shuttles so they could monitor for damage to the orbiters during ascent and while it was in orbit. And that was one of the first big things that was used here. And that was an independent event, right? They were looking at the stressors from aerodynamic stresses, the foam strike, that kind of thing. So here's those aerospace applications. Oftentimes newer aircraft, military, aerospace, space vehicles, and then even some commercial applications now are getting the permanently attached sensors to monitor hard to access structure, like the wing spar. Wing spar inspections have always been a challenging part. It's a very important key structural piece of the aircraft, but up until recently, it's been something that could only be inspected at certain times, right? I've talked about the aircraft I worked on when we did radiography that had to be x-rayed. The main thing we were x-raying, that x-ray was doing wing spar inspection. And the biggest area, one of the biggest areas, was the carry through. That's where the wing spar goes through the bottom, through the fuselage area. It's very hard to inspect in there because it's such thick, heavy structure and so many things bolted together. There's areas you just cannot get to lay eyes on. And so you can either, every once in a while, these were, in this case, it was every C-check, 24 months, the plane would get an x-ray. But if you can put acoustic emission sensors in there that are constantly looking for, constantly trying to sense something, if a crack forms, hopefully you're able to determine that a crack formed rather than waiting until the next time you x-ray it. Other areas, these tend to be high stress areas, trunnions, landing gear mount points. I'm sure that Endeavour airplane, if it had, which I know it didn't because it doesn't, but if it had the Endeavour airplane up in Canada, if it had acoustic emission sensors on the trunnion, you probably would have heard something a couple weeks ago, followed by a lot louder something. Engine mounts, right? Engine mounts are often hard to get to. Engine mounts going up into pylons. Pylons are super reinforced heavy-duty structures. You got all kinds of structure around the actual structure that holds the engine to the aircraft. If you can monitor that for signs of cracking and that kind of thing, it can, that can make a big difference. There have been several plane crashes where the engine came off, right, because of cracked engine mounts. Impact detection, that's what I was talking about with the shuttle orbiter wings, but things for like bird strikes and other stuff like that. Military is using these for impact detection. Fan blade and engine vibration monitoring, right? The CFM 56, that's the one on the 737, the A320, that's prone to fan blade cracking. It's had fan blade cracking problems for years now, right? Something like that. Other area we use it, fluid flow and leakage. So with hydraulic systems, rather than having to plumb in flow meters and that kind of thing, they actually have clip-on ultrasonic sensors that clip on. And based on the rate of flow, it changes the, you can pick up what the ultrasonic signal is. And if you know like the line diameter, the viscosity of fluid, which you do know if you're working on an airplane because you know what size line it is and you know that it has, say, what Skydroll in there. They know what the sound is for a given flow rate through a given tube size of a given amount of material. And so it can tell you if you have what's called internal leakage, if fluid is bypassing seals inside the actuators and inside the systems, and if you have higher flow than what you would normally expect in a system because of that. Fuel systems, oxygen systems, all of those things, any kind of fluid flow, whether it's a fluid or a gas, there are applications for acoustic emission monitoring. So this is an area that's definitely see some expansion, and the fluid flow leakage systems like these can be fixed or portable. The ones we use most often were portable. Actually, I should. Doug's here. I wonder if they have one in South Bend. I need to get. It'd be neat to kind of see one in action. But they basically just hook onto the fluid lines. You turn on the hydraulic pumps, begin moving stuff, and it tells you what the flow rate is, and you know what the normal flow rate of a healthy actuator should be. And if it's exceeding it, it tells you that you're, without having to like bench test the actuator, take it out of the airplane, you can tell if the seals are going bad inside of it. And so you can go from, well, we're going to rebuild the aileron actuator, you know, every so many thousand hours to, okay, we're going to rebuild the aileron actuator when the flow level reaches a certain amount, because that's when we know the seals are bad. And some of them may need to get changed a little earlier, but a lot of them will be able to get changed a lot longer, and they'll save you on maintenance costs and overhaul costs. So